Hello, everybody. This is Abdul Wahab Al Tamar,
I'm Connor McFarlane.
This is Brian Abdelmalik.
and today we're going to present Project 24095, which is a recovery from natural gas. This will be our poster for the design day, and the agendas will be the same for the presentation. We'll be going through the introduction and problem description, materials and methods, results, Aspen simulation, and conclusion. As for the conclusion, it will also include the economics part, which will be presented with the presentation. The first question that comes to mind is why are we recovering helium? Because it's pretty hard to find helium, especially if it's purified in the market, and when talking about money, and that's what makes it very valuable. The targets are so basically we have two systems which are NGL and HRU system, and both of them have a specified targets. As for the NGL recovery, should be 80% or more. Purity should be 99.5% or more. As for the HRU system, helium recovery should be 65% or more. The purity of it should be 65% or more. The target, well, methane should be but the target recovery for methane should be 95% or more, and the target concentration of methane should be 1.30 mole per standard cubic feet. All of that should be achieved with the heating value of 950 BTU per standard cubic feet. This is the PFDs. This is the PFD for the NGL system. As you can see, we've added an NGL loop as a refrigerant. Basically, the refrigerant will cost us less more money because we are already using NGL in our system, as well as we are that also makes us use less propane, which also makes us use less money on that. And then the NGL will be feeding the HRU system, and that's where the helium would be more purified and recovered.
To safely operate our process, we must implement controls such as anti-surge relief valves on all compressors and pressure relief valves on all flash tanks. Additionally, a methane detection system should be implemented inside the enclosed cold box to prevent the accumulation of flammable gas. The anti-surge and pressure relief valves will vent to our flaring system. This system will eliminate methane emissions for methane that cannot be safely recycled. This is a quick life cycle analysis. You can see the inputs and outputs of our system. Something interesting is that at the end of life, we expect the output to contain aluminum contaminated streams because aluminum nitride forms as nitrogen passes over the aluminum's oxide layer. This is more likely to happen in the presence of free carbon, which we can implement elements to detect. And also, it proceeds faster in higher temperatures, and we are operating at cryogenic conditions. So we expect our life to still be long for our equipment. Aspen is a chemical engineering simulation tool, and using user-defined parameters for the equipment, it converges on the correct answers for the flow rates, composition, temperatures, and pressure of each stream. Aspen was used very heavily in this project to converge on the flows and compositions of our streams. And these are the results from that Aspen simulation. They meet all the targets that Abdul talked about earlier. And if you can find the flows of each of these output streams by taking a basis of 4,000 kilomoles per hour for the feed stream.
Now, moving on to the utility table, as we can see, we got the electricity numbers from Aspen. most of our electricity usage came from compressors, especially compressor 101 and compressor 201, due to their high pressure difference. And we also got electricity usage from some pumps. Moving on to the economics, our utility cost came from electricity and refrigeration system, which is propylene in our case. And the production cost, we got the numbers that Aspen has, the production rate, and then we got the raw material price, and then we multiplied it. We got the price for the production cost. And the total maintenance cost, also we got it from Aspen. And the total operating labor cost, we calculated it. The equipment cost, we got it from Aspen, but there are some equipment that Aspen couldn't calculate, so we had to calculate them manually. Also, Aspen uses different material, and we use aluminum alloy 7075. Then we had to multiply the material that Aspen uses by 1.83. And the total direct costs, which include installation costs, we got it from Aspen. Then we got the total revenue, which was 3,343 million, and that gave us a profit of 207 million. Here are some equipment details that we got from Aspen. However, there are some equipment that Aspen couldn't calculate, so we had to calculate them manually, such as condenser 201 and condenser 202, and some and actually exchanger 203B. We assumed it to be the same area and the same numbers as E203A, which was calculated from Aspen. We assumed E203B has the same dimensions as E203A. After checking at startup conditions, it turns out E203B has the same heating duty as E203A. Also, turbo expander 10B was calculated manually, and it's worth noting that we are using aluminum alloy 7075 for all the materials. And thank you so much.